Hi everyone, welcome to Learning Space. My name is Nicole Gallucci. I'm a postdoc with CosmoQuest, and I am joined by my excellent co-host, Georgia Bracey.
Hello everybody.
Has been rocking the show without me quite a few times in the last month, because I seem to be not here a lot.
Stop traveling.
Sorry.
Can't stop the traveling.
Can't stop. Must go to all the cool places and share science with people.
Oh, she's everywhere. She's everywhere.
And don't mind me while I set up comment tracker again.
Yes.
Give me a minute. Okay.
That's something that still mystifies me, so...
It's all good.
But yes, you can comment as you watch the show from a variety of places, and we'll do our best to keep track of them.
That's right. So I am setting up comment tracker. It's already set up. If you're watching this on YouTube, you can send us comments there. If you're watching on the event page, I just got that in there. And I'm trying to put the link from my page, but that doesn't matter as much. Okay, but I've got all those sources. So there's also a new feature in Google Hangouts called Q&A, and so if you're watching this somewhere, you see a little yellow bar that says Ask a Question. There is a separate app for that, so I will try to remember to check that one as well, because it's not in the same place. So you can use YouTube, use Google Events as before, the event pages before, and say hi. And we are going to be talking all about gravity, and maybe, George, you can start us off talking about why we've been thinking about gravity lately at CosmoQuest.
Yes, we've been thinking a lot about gravity lately. We've also been working on this wonderful new classroom unit called Investigate for teachers, middle school teachers that want to do some citizen science in the classroom, and you want to learn a little bit about asteroids. So the NASA Dawn mission recently visited Vesta, and you can help them analyze what they have found there if you go to cosmoquest.org and you try the citizen science project.
It's a pun, guys. Just so you don't know, you can't tell just from saying it, but investigate is a pun on the name of the asteroid that we're studying. So sorry, continue.
Love it. So yes, you can go to cosmoquest.org and do Asteroid Mappers, the Vesta edition, and actually help the scientists look at the beautiful pictures of Vesta and analyze that data. So teachers, of course, would like to get their students to do the same thing, interact with some good data collection activities, see what real science is all about. So we are working on a curriculum to help them bring it's called Investigate, help them bring asteroid mappers into the classroom. So a big part of this curriculum is looking at the early solar system. How did it start to form? Where do we get asteroids from anyway? How did they happen? And a lot of this has to do with gravity. So this whole idea of, how do you teach gravity? What do people think about gravity? It's a very interesting and a very complex idea. So that leads to lots of misconceptions and misunderstandings about gravity. And so we're going to talk a little bit about that today, because our Investigate unit is, at this moment, it's about 13 days of classroom activities and assessments and all that good stuff. And I think it's day 2, early on, you get to do a little bit of fun with gravity.
Yeah.
That's a big player in how our solar system formed.
So I did an accretion activity with Play-Doh on a previous episode of Learning Space. I don't remember how long ago it was, and I took different colors of Play-Doh. It is very fun, and you can go back in the archives and see that one. I think it was when I was talking about... It's whatever episode I had to do all by myself, so it's me rambling for 40 minutes. But I did use Play-Doh to model how accretion happens in the early solar system, and ended up with this glob of hardened Play-Doh that is now all the same color. It's literally, I think, pink, yellow, and blue that have all been mixed together, and it still sits on my desk. So go find that accretion activity that I did. That doesn't explore gravity itself per se, but it does talk about the accretion processes that create the planets in the solar system and in all exoplanet solar system. What is the name we're using for this now? Is it exosolar system? I don't even know. I should ask someone.
Closest we've gotten to anything is early formation of rocky bodies in the early solar system.
Right, but how do we call it? How do we call a system of exoplanets? Is it an exosolar system?
Oh, sorry. I don't know.
I don't know the correct terminology. I should go ask a Kepler scientist. I feel like This is something I should know.
I
All
like
right,
the solar system.
exosolar system. We're gonna use that for the next few minutes until somebody corrects me in the comments. Yeah. So what other? I don't remember off the top of my head what other activities we have on other than the misconception cards, which we'll get into in a bit. What other gravity stuff do we have on that day?
So the first thing is doing the old Galileo, or possible, whether or not he actually did this is, I guess, not totally known for sure. But it's claimed that he did this. He went up to the top of a tall tower and he started dropping things
The Leaning Tower of Pisa in particular.
So something many other people have done since then in the name of science. So he was looking at falling objects and comparing how things behaved when they fell from a great height. And so sort of a mini version of that is one of the first activities. This is something you can do with your students. You can have them, first of all, talk about and think about, what happens when you drop objects of different weight, or different mass, different shape, different size, all kinds of things. So to start to elicit the ideas that they have about falling objects and about gravity, because that's a really important part of education, is to look at what people are already thinking, because we don't just dump information into people's heads, into their empty heads.
What?
Because it would just be too easy that way. People already have ideas about gravity, and of course, growing up on planet Earth, we deal with gravity every day. So, we have a lot of ideas, for better or worse, about gravity that we come into the classroom with. So your students are going to have all kinds of interesting ideas, and you need to sort of get them out there before you can really start to have them learn.
Ah! I fell out.
Juan, and she's back.
I fell out. Okay, we're back on. Continue.
Okay.
Sorry.
So that's okay.
Jeez.
So think about falling objects, all different sizes and shapes of falling objects, and then ask yourself, do they fall at the same rate? Do some fall faster? Do some fall slower? What makes the difference? So talk about that, and then they get to try it out. So they get to get a bunch of different objects from around the classroom, simple objects, and then sort of do their own experimenting, do their own trial and error kinds of things with these objects. So take two objects, put them up at the same height, let them fall, and just observe. Take notes. Do they hit the floor at the same time? If not, why do you think that happens? What do you think's going on? And so they'll get to see things like, of course, air resistance comes into play. So if you drop some sort of like a golf ball and you drop a piece of paper, obviously the piece of paper is going to float its way down gently, to the floor, and the golf ball will just plummet very quickly. So what's going on there is that just how much they weigh, their mass, their shape.
It's a live demonstration. I have hardened Play-Doh and paper right there.
Sure.
Ah! Yeah. See?
So that's to start to sort of tease out what's going on.
I can drop a ninja in a piece of paper? Okay, I'll stop. Sorry.
What happened? We can't see.
Huh? Oh, I dropped them on the floor.
We don't have a view of the floor. Did they hit at the same time?
No, they didn't. There.
Okay.
There. Actually, you can probably hear the ninja hit the table before the paper leaves the field of view. Ah, see? There you go. Science, people. All right.
I know, and actually listening is a good way to tell if your objects are hitting at the same time or not. So do you hear two sounds at impact, or do you hear just one? Because it can be difficult to tell with just your eye, just looking. But you can get an idea of some of the different things that are happening. And then, of course, finally, you can take a piece of paper, two identical pieces of paper, and you can crumple one up, leave one flat, so you know that one, they have the same mass, and then drop them and see what's going on. So two things of the same mass, one's still dropping and hitting the floor quicker than the other one. So that's just sort of a beginning investigation into what's going on with dropping or with falling objects on the Earth. And then we have
spoiler alert, air resistance matters.
Talk about air resistance, yes. And then you can show the nice video. I forget which astronaut it is who did the experiment on the moon. I don't know. Are you Googling? We could Google that real quick, but I can never remember that.
It's Apollo 15. It's David Scott, according to.
Is that who? Okay, I always forget
the Googles.
It was the name, but
it was a hammer and a feather.
Yep. So he took, two objects. One which on Earth the feather would have a lot of air resistance involved in its fall, and the hammer which wouldn't have quite so much. But you take the atmosphere out of the equation, and you let them drop them at the same point at the same time, and you can see really clearly and nicely on his video that yep, they hit at the same time. So you need to take that air resistance out, and then you can get a clearer picture of what's going on. So all of that is in the first activity in Investigate, with starting to investigate gravity.
We show the video.
Yeah, cool.
There's no audio, but he's explaining, I have a hammer and I have a feather. And he says, one of the reasons we're here today is because of a gentleman named Galileo. So we're going to test this. So this is pretty stunning.
I know. I love that he brought a feather all the way to the moon.
It is a falcon feather.
A falcon feather.
And he's going to drop them. Yep, they hit at the same time. Something you cannot see on Earth.
And it's so wild. It just looks so wrong for the feather.
Yeah, it just totally blows your preconception of what falling things are supposed to look like.
Right. That in itself is, worth
Yes, the feather and the hammer just boop at the same time.
Yeah.
Different masses, but the same acceleration. So that's the physics behind that.
Yep. So then we have a nice little card game that we're working on to deal with some of these misconceptions and just some interesting ideas about gravity. So we have a whole list, and if you Google, if you look around, I mean, there's tons of misconceptions that people have about gravity. And, some of them are, I don't know, just more simple than others. Others are more fundamental misunderstandings almost about what's going on. So misconceptions can be very hard to get rid of, because the more fundamental ones are based on our everyday experience that we've had for our whole entire life. So it's really difficult to counteract something you seem to experience correctly, you think, every day, and you've got in your mind sort of a really nice explanation for how this thing called gravity works. And then you get into the classroom and you bump up against this other explanation, from your teacher that doesn't fit with your own experience, your years of experience. And so what do you do with that? So it's sort of that conflict that starts the whole learning process going. And so if you don't have enough good experience and enough really hands-on experience with that new concept, it might sort of chisel its way into your brain a little bit, but it's going to get kicked right back out if you don't really wrestle with it and work it into your own, system of how you understand that concept. So that's why, lots of activities are good, hands-on experience is really good, because that lets you really wrestle with the concept and make it a permanent part of your way that you understand how the world works. So,
we have a comment from, so just to let you guys know, my comment tracker's now broken, but I'm trying to follow on the event page on YouTube anyway, because I love you guys. So if you have certain interesting gravity facts or misconceptions you want to share with us, that would be awesome, and help us out, maybe help us with the activity. We are collecting gravity misconceptions. Guido Bubra says, we need to replicate that experiment when we get back to the moon one day, preferably on live HDTV. And we now have the bandwidth to do that. So we can have our future astronauts. Yes, so you can't actually do that experiment. I guess okay, so your typical student cannot do that experiment. You know, you can, if you have a vacuum chamber, access to a vacuum chamber, you do that experiment. That one's a bit tough. But you can play. So what I discovered when I was taking physics in high school is you can play with the idea of gravity and acceleration on an elevator. So if you happen to live in a building or work in a building where an elevator is not used all that much and you can get away with this, is to take a bathroom scale into an elevator and see as the elevator is accelerating and decelerating when you go up and down, how it actually changes the reading on the scale, and what does that mean? So this is, I didn't actually bring a bathroom scale into an elevator, but I did jump at the moment of acceleration and deceleration in an elevator in a hospital I was working at the time.
Do you want to weigh yourself when you're going up or going down?
Either one. It's the and when you're it's the acceleration and deceleration at the beginning and end of the trip is when it makes a difference. So the constant velocity of the trip up or down doesn't matter, but when you're going up or down, whether you're accelerating up or decelerating as you go up will actually change the measurement on the scale. But like I said, you can feel that effect if you jump at the right time. So for those of you who have been in an elevator with me and I've jumped randomly, this is why. I do funny things like that.
I'm amazed that actually works.
It does. It totally works. It totally works. You can feel the difference.
Tried it, but yeah, red.
I actually got a group of people to do it at Dragon Con. So.
Lovely physics problems written all about that.
I got a bunch of people to do it at Dragon Con.
You did?
Well, after the day after. Well, the last night of Dragon Con when most people had left. We were doing superhero up. We literally ran out of stuff to do, so we were riding the elevators up and down. And I had everybody jump to feel the acceleration and deceleration differences. I was doing physics. It was fun, but that I do not recommend you put all your students in an elevator. But this is it's a separate activity you can do with your own child or yourself for your own curiosity to play around with the idea of acceleration and gravity. But anyway, back to the cards. This has been my thought processes today. So
we're collecting misconceptions.
Yes.
Or just alternate, some people call them alternate conceptions because misconception sounds kind of heavy and negative, and and it's really not that it's a bad thing because everybody has misconceptions about everything. It's how your brain works, how you collect information. Sometimes the misconceptions are actually helpful. We manage to get out of bed and get to work and do all our things, and operate in a world of gravity all the time. So apparently, you can be relatively successful in life and have these misconceptions hanging around in your brain. But, if you want to investigate and you want to go further and learn more and think about all these cool ideas, then, you have to do a little, just do some activities.
It's interesting that you say about living and working in gravity, you could just handle it without thinking about it. And it's really interesting to hear the experiences of astronauts who spend a significant amount of time on a space station because they come home and they can't handle gravity anymore. They'll, once they get to the space station, they have to be able to adjust to the fact that, when you put something down, it doesn't stay where you put it. It floats off. Or that, in order to turn a door handle, you're going to, turn yourself. And they slowly, they actually have to adapt to a completely different environment. And when they come back home, they can't, they'll walk into things because they're just not used to dealing with gravity.
You have to readjust. Right. Yes, there used to be, I'm sure it's on YouTube somewhere, there used to be a really funny NASA video that I would show my 5th grade students, and it was, it was Sally Ride, and it was way back. But it showed astronauts on a space shuttle and how they, lived and worked, and it was kind of funny, and they showed all the funny little gravity or microgravity effects of, liquids forming little, spheres and things and floating around. And yes, things, you have to tether things because otherwise they float away. And of course, the hair flying everywhere, and people being, one person eating, right side up according to our perspective, and the other person just next to them, upside down. All that fun. So it's it's a lot of fun, but it really does challenge, how you think about things and look at things.
I was watching them do a live Q&A from the ISS a little while ago, and it was so funny because they're standing there, they're floating there holding the microphone. I think it was actually Chris Hadfield. So he's holding the microphone, and then he goes to demonstrate, and he just lets go to demonstrate something with his hands. And the microphone's just there, and then he just, casually picks it up with the other hand. I'm like, that just happened. That is so cool. And of course, though, we're talking a lot about space station and gravity in space and the weightless or microgravity environment, and that's one of our big misconceptions.
Right? There's no gravity in space.
Mm-hmm. False.
Correct. All right. What do you get? You get a ninja.
I get a ninja. These have been showing up on our desks. There's a little desk war going on back here.
All right.
There's an alien, too. This is more appropriate. So, yes. So, of course, there was gravity in space. And, in fact, the gravitational pull of... So, most of our work by astronauts and cosmonauts and taikonauts is all being done in low Earth orbit. So, it's actually not that far above the surface of the Earth, relatively speaking, that all this stuff is happening. And so, that distance from the surface of the Earth, the gravitational pull of the Earth, is only slightly reduced compared to what we feel here. So there's just as much gravity in low Earth orbit where astronauts are working as there is on the surface of the Earth. So the question is...
like 88% or almost 90%.
Oh, is it? I thought it was... Yeah. So it's something like 90-something%.
Most.
Right.
You still have most of the effect. So, so what's going on? And again, you can understand how people get that misconception. Especially because you watch the videos from space and things, and that's like the coolest, most impressive thing you notice is, people can float around. And,
and we call it weightlessness and microgravity, which are just complete misnomers.
So sometimes the names of things, the vocabulary is what leads us astray in really getting a good understanding of these concepts. So it's not a surprise at all that students and adults, students of all ages, get these misconceptions from looking at these videos, hearing the words, and and you want to believe your eyes, and it makes perfect sense. It makes perfect sense because most of us don't get the thrill and the fun of going up in space. So for us it works.
So the question is then, why does it appear weightless? Why do people and things appear weightless in low Earth orbit? And so the answer to that is that basically the capsule that they're in, the structure, the space station, the shuttle, whatever they're in, is in free fall around the Earth. So it is falling towards Earth, but it's orbiting at a quick enough speed that it's going to go around the Earth and not actually hit it. This is a good thing. So it's in free fall around the Earth, and then the person inside it, here's my spaceship, and it's going to be alien. Here's my astronaut. They're both in free fall around the Earth, and so their acceleration is the same as they're both in free fall, and so relative to each other, the alien is floating in the space capsule, but it's feeling just as much, it's feeling the same gravity that, almost the same gravity it would feel on the surface, and feeling the same gravitational pull as the spacecraft, and because they're both in free fall, that is why you get the feeling of weightlessness. And this is, of course, simulated by aircraft that do parabolic flight paths, and so they do a lot of testing.
Also, be fun to do. That would be a great second choice if I can't get into space.
That is a lot more affordable, actually. I don't. It's way out of my price range, but it's a lot more affordable than tickets.
How affordable are we talking here?
Yeah, we're still talking expensive, but it's a thing. I mean, it's a thing people do for fun. Is like you could book a flight on the, I don't know what it's actually called, but I know the KC-135 is the one that they use at the Kennedy Space Center. So yeah, we have a great comment from Guido saying Chris Hadfield, so the astronaut we were talking about before, who was briefly the captain of the International Space Station, or what do they call him? Captain, chief? I don't know. The guy who was in charge. Commander. That's right, commander of the International Space Station. He's a Canadian astronaut. He said something. He had to relearn how to play guitar in Zero-G because the instrument feels much different. It doesn't pull down. So when he made that really cool Space Oddity video and did the guitar chords for that, he had to relearn how to play
I
the
almost
instrument.
imagine you'd have to like tether it to yourself. I mean, to like almost tie
it was probably like floating over him.
Because you would try to. I never thought of that. See, that's great.
But he thought he played better in the space station than he does on Earth. That's his opinion. That's his own opinion.
Singing better in the shower,
Yeah, right. Like you sing better
in a different environment, and then hey, it's all good.
Right.
Well, I wanted to mention too. I don't know if you've ever seen the video called "A Private Universe."
That does not ring a bell.
Okay, this is a classic. You can Google it, of course. And unfortunately, the URL is a bit long, but I could put it on the event page afterwards. But this is, it's a video that was produced by the Harvard-Smithsonian Center for Astrophysics. It's back in 1987, so it's kind of a classic video now. But what they did, they went to a Harvard graduation ceremony. So you can imagine that, Harvard, wonderful institution of learning, and so you get the idea of all these really smart people. They're graduating from Harvard. These must be, the cream of the crop kind of thing. And they asked the graduates at the ceremony a couple of questions about astronomy. And one of the questions was, why do we have the seasons? Why, for example, is it hotter, in the summer, at least in the northern hemisphere, than it is, in the winter? And so why are the seasons there? And everybody they talked to had this idea of, well, it's warmer in the summer because the Earth and its orbit is a little closer to the sun than it is in the winter. And so, there was this big misconception going on. And that was one of the first, at least for me, one of the first times, I really started to think about that. Here are these intelligent people, and yet there's still these misconceptions. And so I guess it's a great video to watch, just because it is, it's kind of considered a classic now. But it also lets you know that, intelligent adult people have misconceptions. And it's really fun to think about and make lists of misconceptions, but you have to remember that most of the time it's ideas that people have gotten, that really make sense to them and really come from their own experience.
And you can even teach somebody
so you have to
the
really
answer. Right, yeah, and they'll revert back to, we all will revert back to our misconception if you don't really break it down. And for the seasons one, the one that I think is the kicker for that is if you say, okay, most people are aware of the fact that when it's winter in the northern hemisphere, it's summer in the southern hemisphere, and vice versa. So if you ask them the question about the seasons, and they tell you, well, it's when it's closer or further, then say, okay, well, do you know that blah, 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 about the different hemispheres? How does that fit into that model? And that moment, it breaks, right? And so that's what you need to do. You really need to break, this comes out of years of educational research. You need to break that misconception in a way that you realize, oh, that can't be the case because I know this other fact and they're inconsistent, and now I have to build it just shattered, and I have to build a new model. And I think that's the one, because people are aware that the seasons are different in the different hemispheres, and until you actually make them connect that with their misunderstanding about the Earth being closer, and that's why it's summer. That doesn't, unless half the Earth is, it doesn't work that way. So, in fact, we're closest to the sun in January, so it's winter in the northern hemisphere. But most people don't know that.
Right, and I remember for me, that fact just made it amazing for me.
Right.
So obviously, what else is going on here?
Right.
So So that's
the breaking moment, is when you remind them that the different hemispheres have different seasons. That's what helps people break that down. Yeah.
So let's see. Another good misconception.
Well, actually, there's some here that were truths, not falses. that I didn't know much about. So one of these cards, and I know we're totally giving this away. It's like spoiler alert. But one of them is gravity guides the growth of plants. And this is actually a true statement, not a misconception. And I actually had to dig a little deeper into why that is. And apparently they recently discovered that there are these special cells in the tips of roots of plants. So, I mean, they tested this in all kinds of ways. I mean, for centuries, you know, you put a plant in the soil and it's dark. How does it know roots go down and shoot goes up?
Yes.
And they tested this with different ways. And so they did, you know, you do the cup upside down and the plant will still grow out the correct way. I don't remember what scientist did this, but they actually put a bunch of seedlings on a rotating table. And all the seedlings grew out, following the centrifugal forces as if it was gravity. So clearly, plants can sense gravity, and it wasn't. I think it wasn't until more recently they discovered that there are special cells in the tips of the roots that have these little pebble-like structures in them, and so the little pebble-like structures are at the bottom of the cell, where in the direction of where gravity points down, and so that tells the plants. That way it's down, that's where the roots go, up is where the shoot goes. I just learned this today, so this is fascinating.
Your own gravity sensor.
It has, yes, plants have gravity sensors in their roots, and there's a name. Statoliths, so the little, like, tiny structures. I'm probably screwing this up, I'm sorry, botanist, please correct me. But I just learned this today, and that's how plants actually are thought to sense gravity. And yeah, I totally want to try that rotating table experiment and watch the seedlings grow outwards.
Yeah, I know. We were just talking today about needing a turntable and how it's too bad that there aren't enough turntables around anymore. So there's another great application for turntables. You've got one in your basement, get it out.
Yes.
Or in your attic. Yeah. Yeah.
So we have a question from Janelle Duncan. Does gravity change when you are at different elevations? That is a very good question. And so just as if you're in low Earth orbit, you're some distance above, so actually it's measured from the center, your distance from the center of the Earth determines the gravitational force that you feel. Indeed, at higher and higher elevations, you are some larger distance from the surface, so the acceleration due to gravity is slightly less if you're at a really high elevation. Now, of course, it's tiny, really hard to measure, but it is actually an effect in that if you're at 16,000 feet, the acceleration due to gravity is going to be slightly smaller. Now, 16,000 feet sounds like a lot, but that's like, you know, the skin of the Earth, whereas the bulk of the Earth is so much bigger. So yes, it does actually lessen, but by such a tiny amount, we don't even. And that's the problem with relying on our everyday experiences, right? Is that they don't measure things accurately.
Right.
We're limited. So thank you, Janelle, for that.
That's a great question.
Yeah.
Yeah. So one of my favorite questions about gravity that I ever got, and I think it's on our list somewhere, is the idea of if you could bore a hole through, well, either at least down to the center of the Earth.
And that, well, yeah, through
all the way through, right? Mm-hmm. Okay. And then if you dropped, or what would happen if you dropped something down that hole?
Mm-hmm. Do we want to give the answer, or do we want to just let our audience?
It still kind of boggles my mind, and I don't know. I don't think we should say the answer. But
okay, I like that.
I know.
This. I mean, if you've taken an intro physics class, this has probably come up. You've probably had to calculate this.
I know. Yeah,
I will point out that this was another thought experiment. Actually, so again, researching this stuff today, this is a thought experiment that has been done throughout the ages. And I think Galileo was the first person to really get it, and then Isaac Newton was the first person to mathematically show that the answer was the answer, and that is true. Of course, you have to neglect air resistance and running into stuff when you think about this, but yeah, assume you drive. Okay, also, one other complication.
It's easy. You can neglect whatever you want.
Yes. Assume a spherical cow. So this pebble, and also if you assume assume either it's not rotating or it goes down this axis of rotation, because rotation will change it, and that's also Newton calculated, which is pretty cool. And so yeah, it's an interesting thought experiment. Of course, never done as a real experiment because we still haven't even gotten to the mantle, I think.
Oh.
Of the Earth. There was a project called.
We hadn't gotten very far, but yeah.
Yeah, there was a project called the Mole Hole Experiment. I kid you not. I don't remember what it stood for, but mantle was in it. It was a project to reach the mantle of the Earth, and like they still have not done it. So mole hole. I remember this from my Geology 101 class. Thank you, Dr. Erickson. So we have cannot drill through the center of the Earth technologically, but this thought experiment can be done, and it can be proved mathematically what will happen to that pebble. So we will leave that as an exercise for the year. I hate that.
It boggles the mind. I know. But it's a great one. It's a great one. So
it is a good one. Yeah, so I'm glad we included that one. And I started to get into way too much detail in my description and had to get rid of it. Because I know I can submit that and
easy to do.
Kathy and Alan are going to be like, no.
Easy to do.
TMI.
Yeah.
TMI.
Okay.
Ooh, another one I like. This is another true or false statement. Although you cannot feel it, there is gravitational attraction between you and the person sitting next to you. Is that true or false? Tell me, George, is that true or false? Am I gravitationally attracted to this ninja?
I'm sorry to say yes. And he loves you too.
This is he's got a knife. I should be careful. This is another place where our common everyday experiences don't quite measure up to reality. You can, I mean, we both have mass, and there is a finite distance between us. So there is actually a very tiny gravitational force between me and the ninja. Now, of course, if me and the ninja were floating about in space, not near any other object with mass, then we would be gravitationally pulled together. But because we are both gravitationally pulled to the Earth, that is by far the dominant thing. But there is a gravitational attraction between people sitting next to each other in class, and we thought that'd be a cool factoid to throw in.
Let's take the opposite. So one of our things talks about the Andromeda Galaxy, you know, something much further away from us than the little ninja.
Right.
Are we attracted to the Andromeda Galaxy, and is it attracted to us? Are we?
Actually, it's the wrong direction. It's like down here.
Where is it?
It has not risen high enough to be visible during my my public observing nights. So. Not there yet. Anyway, go on. Sorry.
Yeah, no. So that's, you know, something sort of the other, I don't know, extreme or the other side of the coin kind of thing. So, so smallish things that are close, you know, yes, there's still that force of gravity acting. But what about a really huge thing that's very far away? Does that mean, is it so far away that, you know, there's no effect anymore because it just... You know, it's another common thing that people think is, you know, you get far enough away, whatever effect you're talking about, whether it be magnetism or, you know, electricity, you know, it kind of dies out because you're just far enough away at some point. And no.
Only if the distance is infinity. If it is actually mathematically infinity, and we do live in a finite universe, you do get the gravitational attraction of everything in the universe. It is not zero. It is to the point where it is realistically negligible. Now, of course, this is ignoring the fact that at some point, right? I actually had to put ignoring dark energy, because at some point, the acceleration of the universe will be the actual acceleration, the shape of the frame of the universe will be greater than the speed of light, which is the speed of gravity. There's a lot to unpack there, but at some point that will no longer be the case. But within the observable universe, of course, we have not reached that yet, and so yes, we are gravitationally attracted to everything in the universe. There's a lot of caveats there. I'm sorry.
There are, I know. And that's where it gets
that's why I just said ignoring dark energy.
Right. You know, I mean, it's fascinating, but it's also very frustrating because part of you just says, you know, I just want to understand this gravity thing.
Yes.
And then,
to be simple.
Typical with life, you know, it's way more complicated than we would like it to be, but you know,
but that's okay.
The way it is, yeah. So that's the challenge of getting your mind around it. So
we have a comment from Peachy Holyfield, who's the author of the book that is my mousepad. Yay! He said he just saw the ooh, I'm jealous. The movie Gravity, which is a sci-fi, one of this new trend of sci-fi stories that is not too far in the future, and so it's just barely on the edge of what's possible today. He apparently got to see it at a pre-screening event and can't wait to talk about it. So this is kind of a horror thriller set in space. I know the trailer was like amazing. It's what goes wrong in in space in the absence of your normal gravitational environment. So yeah, I'm jealous that he got to see it already. So if anyone else has seen Gravity, kudos, and I'll try and find a screening
Yeah.
here.
Something to look forward to.
Yes,
Excellent.
but I cannot talk on that movie because I haven't seen it yet. So yes, this is not about the movie Gravity. I'm sorry if you tuned in and thought we'd be talking about the movie. We're talking about the actual
later.
course.
Maybe later. All right.
Some other time.
Yeah. All right. Good. All right. So we want to pick out another one.
Sure.
Let me find
What
it.
do we got?
Oh, let's see.
Ooh, this is a good one.
You got one?
Because it's an interesting one. The statement was planets with thin atmospheres have little gravity. Is that true or false?
Oh, okay.
That's a tough one to unpack.
True or false?
Yeah. So planets with thin atmospheres have little gravity. So the statement as it's written is saying, well, if it has less atmosphere, then somehow the gravitational force is smaller, and that's not necessarily true. So I would go ahead and put this statement as false. The atmosphere itself does not affect the gravitational pull of the planet. Your gravitational pull depends on the mass of the planet beneath you, not the mass of the air above you. That affects the air pressure that you feel, but doesn't affect gravity. Now, the connection here is that often what can happen for smaller planets is that smaller planets have lower gravitation on their surface, and so they're more likely to lose their atmosphere. However, that's not a strict one-to-one correlation. For example, Venus and Earth are about the same mass and radius, but Venus has way higher surface air pressure. It has a much thicker atmosphere than the Earth does. But they're the same mass and pretty much the same mass and radius. There are other factors like distance to the star, there's the temperature of the planet based on the distance to the star, whether or not there's a strong magnetic field has a lot to do with it. And so that statement as written is false, but you can see why someone would make that connection.
And even, kids, we always talk about the moon and does it have an atmosphere, and we used to just simply say, well, no, it doesn't, and now, we can maybe talk a little bit more about that too, so maybe there's some traces of stuff up there, but either way, we always say it's too small to have really, substantial atmosphere. So, you make that connection between, small thing, hardly any atmosphere. So you sort of overgeneralize in a way, or just make a connection that isn't based on having all, of the information. Like you say, so much more going on. And then it's very, easy to take that sort of relationship that you think is true and then transfer it to other contexts and overgeneralize, and before you know it, you have a really deep-set misconception about the relationship between gravity and atmosphere. So, these things, I think almost what's as fascinating as thinking about them is thinking about how they formed in the first place, these misconceptions. So, to me, it's very interesting to, try to figure out how people think, how that misconception could have gotten there in the first place. To see all the different things, because that's actually very fascinating too.
So we have a question from on YouTube from JeffAir101. Is gravity affecting the Voyager probe? And if so, why doesn't it fall back? So we recently had news that yet again Voyager left the solar system. Depending on your definition of solar system, we debated this on the Weekly Space Hangout. But the Voyager space probe is moving further and further away from the sun. So the sun makes up most of the mass of the solar system. And so that's the gravitational field that it is most affected by. However, its orbit is such that it's moving at a velocity that is great enough that it can escape that gravitational pull. And this actually helps define what the escape velocity of something is. How do you get a rocket off of Earth and to the moon? It's got to escape the gravitational well of Earth to some extent, at least as far as the moon. And so you can actually calculate that using the mass and radius of the object you're trying to escape. So taking its gravitational field into account, you have to move at a velocity that is fast enough that the pull of gravity is too weak to be able to pull it back. Now, gravity is the weakest of the fundamental forces, so it turns out it's not that hard. Build a rocket, off you go. Okay, that's oversimplifying, but it is the weakest of the fun. being
Don't be giving people misconceptions,
I'm
Nicole.
being flippant about everything. No, it's really expensive, really, really, really hard to do. But gravity is the weakest fundamental force, and so yeah, you can get an object moving fast enough, and this is the same thing for things that are orbiting. There's a certain speed you have to reach in order to be able to orbit the Earth and not fall down and crash onto the surface. You need to be going fast enough that you miss the surface and keep going, basically. So that's how I think of it. And if you're doing escape velocity, you have to be fast enough that you are escaping the gravitational potential of Earth, or in this case, the Sun. So that's why Voyager's speed, the speed that it was given as it was sent off into the outer solar system, is that incredible speed is what allows it to not fall back as a function of gravity.
Yep.
Yeah. So, and I don't remember what that speed is, and I totally looked it up during the Weekly Space Hangout when we talked about it, and it's completely gone from my brain. So, it was there and it's gone. But it is fast enough that yes, it escapes the gravitational pull. I mean, yes, it's still feeling the gravity, but it's still moving fast enough that it's not bringing it back. It's just going. It's gone. It's done. It's just gonna keep going. So, thank you for that question.
Well, let's do this. This is one I actually don't know a lot about. So we had plants with gravity sensors, sort of, before. So apparently bacteria can also get in on the gravity sensing action. We have one of our statements, without gravity, some bacteria get tougher.
Yes.
And I have no idea.
I had to look that one up, and I was, because
that was a totally new one for me.
And I put that exact statement in Google and found where they got it from. There was a study done in 2007 of salmonella bacteria, and I'm not sure if it was on the International Space Station or on one of the shuttle missions, but it was, in a low microgravity environment. They tested how virulent or how harmful salmonella bacteria are. It turns out they are 3 times more virulent in a microgravity environment, and they tested this on some poor mice, which ate food tainted with salmonella. So with less salmonella, God, I can't think of the word. With less salmonella bacteria present in the food, and the infection happened faster, and so it turns out salmonella is
much more potent in space.
More potent in space, and they're not sure why, but they did notice that the proteins and the genes in salmonella acted a little bit differently in that environment. They're just not sure exactly why it all happened that way.
Cool.
But yeah, so not only
potential there, actually.
Yes, exactly. Right there. Somebody write that story.
Yeah, I'm thinking Andromeda strain, but
that's exactly what they referenced.
That's a classic. Did they? Okay. Ooh,
in the article about it, yeah, or in the article about the paper that I found, that's what they.
There's something about space that makes things tougher.
Except humans. Except humans, because as one of our statements.
There's another, yeah.
Yeah. What did I? Being on the space station, so in a microgravity environment, can cause problems such as bone and muscle loss, and this is again a problem for astronauts who are in low Earth orbit for quite a while. Your body decides, oh, I don't need all this muscle, I don't need to stand, and actually breaks it down and starts using it for other things. Yeah. And same for bone as well. And so astronauts have to keep up a very vigorous exercise program in a microgravity environment in order to not fall down as soon as they come back.
But I think people get taller, right?
Do they stretch out? I don't remember. Oh, yeah, no, I think I've heard that one, because I'm a short person.
I pulled that out of like 20 years ago or something. I have no idea if that's really true, but I used to hear that a lot. Maybe
you get a bit taller? Yeah, I think people have specifically said that to me because I'm 5'1".
Much taller, right? We're going to say, no.
I'm like 5'1" and a half in space.
Taller, right. Yeah.
And other they're always sound like they have a cold because all the fluid in the nasal passages flow. And so astronauts are constantly stuffy, and they can't smell anything in space. Yeah, there's all these weird little effects that happen because our bodies evolved in a 1G environment. That's how they work well.
Where we like to be.
Yeah, and that is a significant.
Long-term.
Yeah, that is a significant issue for long-term space exploration. And so, do we send our ship spinning so that it simulates gravity, or do we, what do we do? What do we do? Yeah, I've heard some really crazy stories of astronauts who just, especially during some of the Mir space, spent a year and a half on Mir.
Long time.
You know, they were wheelchair bound when they came back home, and it took them a few days to get their strength back and people would walk. That's like really serious.
Yep.
So.
Yeah.
Oh.
Oh, I don't know.
I'd still go.
Well, I know. Yeah.
Oh, and does the speed decline? So about the Voyager probe question, does the speed decline? I think it's far enough out at this point that it's the gravity is so low that it's not causing it to slow down. So it's pretty much just going to coast now at this point. But yeah, they would have if it was staying close to the sun, they would have to keep speeding it up in order to keep it from crashing down.
That's a great question. A good question.
Yes.
Yeah.
Yes, good questions. Yes. Yes, Veer. All right. Watching a lot of Babylon 5. Yes.
Together. Okay, yes.
Yes, Veer. Any last comments on gravity?
Through our list, I don't know. I think we've hit some of the big ones, a lot of the big ones, and I don't want to give them all away either.
Yes, let's not do that. But when will so Investigate is still in the process of being worked on. We're doing, if by some chance you happen to be in the area near Edwardsville, Illinois, we are doing a teacher focus group on Columbus Day, October 14th. So please email us if you are local and want to do that on your day off. Play with us, play science with us.
Yeah.
We'll be testing out some of these activities with the teacher focus group, and at that point I think we'll be submitting it for educational review with NASA.
Yep, with NASA, it goes through NASA review, and actually even if you're not local, if you would like to try out parts of this unit, you know, we just need people that can pilot something in their classroom too, and so we can email this baby right out to you, try out a little bit in your classroom with your students. It's targeted for middle school. You know, a lot of it could be upper elementary, depending on how comfortable you are as a teacher with the material. It can certainly be used in high school as well, because as you've noticed, these concepts can really be unpacked, and there's adults that still are grapple with the idea of what gravity is all about. So certainly you can do a lot of good stuff with high school students with this. So if you are anywhere and you would like to try out parts of our new unit, we would love to have you do that and give us your feedback all over email, electronically. That's wonderful. So
yep, it's up on it's up on her screen.
Would like to do that. We'd be really grateful for that. And then yes, sometime early next year, it should be finished and out and available. So at cosmoquest.org.
So the email's on her screens, educate@cosmoquest.org, because my Google Toolbox is broken. educate@cosmoquest.org. We also have a newsletter, which we should be sending out because it's the end of the month already.
Yes.
We should do that at some point this week. If you go to Educator Zone, if you go to CosmoQuest, up on the top bar, it says Educate in the menu. Come down, Educator Zone. It's cosmoquest.org/blog/Educator Zone, but just look for that. That is where we post all of our teacher materials, links to our educational partners who also have awesome materials like the Galileo Teacher Training Program and Dark Skies Bright Kids. And there's also a newsletter. So we have a monthly newsletter specifically for educators that comes out the end of every month. There's a sign-up form on that webpage there, and so you will get stuff from us every month as we put stuff out. And so it'll be links to Learning Space, it'll be links to the new stuff that we're piloting, and yeah, like you said, early next year, and definitely in time for the NSTA meeting in, when is that, March?
It's either March or early April.
April, right, because it was Yuri's night last time, it was April. Anyway, with the name Investigate came out of a conversation. So our two curriculum developers and I were at NSTA in San Antonio, and because the abstract deadline for the meeting is exactly a year in advance, we're sitting in the hotel after NSTA trying to come up, we knew we were going to do a unit about asteroids, and we're trying to come up with a title for this abstract and Investigate. I think that was Kathy's husband who came up with that one.
I don't know, because he is good.
Text message.
He's very good at naming things.
And so that's where we're like, all right, we're calling it that.
That's perfect. It's perfect.
So if you happen to be at the national NSTA meeting, we'll be demoing stuff there too. So it's pretty cool.
A lot of good stuff coming up.
Yep.
And send us your gravity misconceptions.
Yes, that would be cool. We can add them to this card set and grow that a bit and make more work for me because I have to write the explanations why things are true or false without getting too long-winded.
Keep it simple.
Ooh.
Yeah, you can do it.
My brain is everywhere today. All right, thank you guys so much for joining us on Learning Space. Let me check the comment sources again. I think we're good for now, so all the comment sources. Thank you guys for joining us on Learning Space. The next hangout is Friday, noon Pacific, 3 Eastern, the weekly space hangout. I missed last week's. I'm sure it was a lot of fun. Our group of astronomy journalists and wannabe journalists like me, pretend journalists, talk about the top stories in space and astronomy from the week, hosted by Fraser Cain. And on Sunday night, I think they're starting at 8:30 Pacific. They might be pulling it back earlier soon. I'll have to check. Fraser Cain and Scott Lewis do the virtual star party, and so you totally want to check this out. Especially if you can't get out to a star party near you locally, you can sit at your computer and look at pretty pictures of the sky from our amateur astronomers all over the country and all over the world.
You got bad weather, it's always good viewing on the internet.
It's always good. It's clear. So actually, there's been a couple of nights where it was cloudy for everybody who was available. And
no.
But that's because there's a lot of guys on the West Coast. Yeah, and it depends on who's available, who's got, kids, jobs, all those things. So yeah, it's rarely, but it has been canceled a couple times. But usually it's on. And then Monday, I think Fraser and Pamela are back to doing Astronomy Cast. Pamela's back in the country, so I think that's happening again.
Okay.
So that's our usual weekly lineup of hangouts. All right, so thank you, Georgia.
All right, thanks, Nicole. Welcome back.
Yay.
And we'll see everybody next week.
See you guys next week.
Bye-bye.
Bye. Oh, what are we doing next week? I want to promo next week. What are we doing next week? I don't remember.
I don't know.
Wait. I haven't sent out the newsletter yet, which is why I haven't been thinking of it. Oh, we're talking about the blog from the Hubble Candles Project. So we're talking to a couple of astronomers who translate their findings for the general public on a blog, which is awesome. So we met them at the ASP a couple months ago. So yeah, it'll be good. Excellent. We'll carry some dot astronomy love with that too. So all right.
Yeah.
Thanks, everybody.
Good. All right. Bye-bye.
Bye. Hi, everyone. Welcome to Learning Space. My name is Nicole Gallucci. I'm a postdoc with CosmoQuest, and I am joined by my excellent co-host, Georgia Bracey.
Hello, everybody.
Has been rocking the show without me quite a few times in the last month, because I seem to be not here a lot.
Stop traveling.
Sorry.
Can't stop the traveling.
Can't stop. Must go to all the cool places and share science with people.
Oh, she's everywhere. She's everywhere.
And don't mind me while I set up comment tracker again.
Yes.
Give me a minute. Okay.
That's something that still mystifies me, so...
It's all good.
But yes, you can comment as you watch the show from a variety of places, and we'll do our best to keep track of them. That's
right. So I am setting up comment tracker. It's already set up. If you're watching this on YouTube, you can send us comments there. If you're watching on the event page, I just got that in there. And I'm trying to put the link from my page, but that doesn't matter as much. Okay, but I've got all those sources. So there's also a new feature in Google Hangouts called Q&A, and so if you're watching this somewhere, you see a little yellow bar that says Ask a Question. There is a separate app for that, so I will try to remember to check that one as well, because it's not in the same place. So you can use YouTube, use Google Events as before, the event pages before, and say hi. And we are going to be talking all about gravity, and maybe, Georgia, you can start us off talking about why we've been thinking about gravity lately at CosmoQuest.
Yes, we've been thinking a lot about gravity lately. We've also been working on this wonderful new classroom unit called Investigate. She's back.
I fell out. Okay, we're back on. Continue. Okay. Sorry.
So that's okay.
Jeez.
So think about falling objects, all different sizes and shapes of falling objects, and then ask yourself, do they fall at the same rate? Do some fall faster? Do some fall slower? What makes the difference? So talk about that, and then they get to try it out. So they get to get a bunch of different objects from around the classroom, simple objects, and then sort of do their own experimenting, do their own trial and error kinds of things with these objects. So take two objects, put them up at the same height, let them fall, and just observe. Take notes. Do they hit the floor at the same time? If not, why do you think that happens? What do you think's going on? And so they'll get to see things like, of course, air resistance comes into play. So if you drop some sort of like a golf ball and you drop a piece of paper, obviously the piece of paper is going to float its way down gently, to the floor, and the golf ball will just plummet very quickly. So what's going on there? Is that just how much they weigh, their mass, their shape?
It's a live demonstration. I have hardened Play-Doh and paper right there.
Sure.
Ah! Yeah. See?
So that's to start to sort of tease out what's going on.
I can drop a ninja in a piece of paper? Okay, I'll stop. Sorry.
What happened? We can't see.
Huh? Oh, I dropped them on the floor.
We don't have a view of the floor. Did they hit at the same time?
No, they didn't. There.
Okay.
There. Actually, you can probably hear. You can probably
teachers, middle school teachers that want to do some citizen science in the classroom, and you want to learn a little bit about asteroids. So the NASA Dawn mission recently visited Vesta, and you can help them analyze what they have found there if you go to cosmoquest.org and you try the citizen science project.
It's a pun, guys. Just so you don't know, you can't tell just from saying it, but investigate is a pun on the name of the asteroid that we're studying. So sorry, continue.
Love it. So yes, you can go to cosmoquest.org and do Asteroid Mappers, the Vesta edition, and actually help the scientists look at the beautiful pictures of Vesta and analyze that data. So teachers, of course, would like to get their students to do the same thing, interact with some good data collection activities, see what real science is all about. So we are working on a curriculum to help them bring it's called Investigate, help them bring asteroid mappers into the classroom. So a big part of this curriculum is looking at the early solar system. How did it start to form? Where do we get asteroids from anyway? How did they happen? And a lot of this has to do with gravity. So this whole idea of, how do you teach gravity? What do people think about gravity? It's a very interesting and a very complex idea. So that leads to lots of misconceptions and misunderstandings about gravity. And so we're going to talk a little bit about that today, because our Investigate unit is, at this moment, it's about 13 days of classroom activities and assessments and all that good stuff. And I think it's day 2, early on, you get to do a little bit of fun with gravity.
Yeah.
That's a big player in how our solar system formed.
So I did an accretion activity with Play-Doh on a previous episode of Learning Space. I don't remember how long ago it was. And I took different colors of Play-Doh. It is very fun, and you can go back in the archives and see that one. I think it was when I was talking about... It's whatever episode I had to do all by myself. So it's me rambling for 40 minutes. But I did use Play-Doh to model how accretion happens in the early solar system, and ended up with this glob of hardened Play-Doh that is now all the same color. It's literally, I think, pink, yellow, and blue that have all been mixed together, and it still sits on my desk. So go find that accretion activity that I did. That doesn't explore gravity itself per se, but it does talk about the accretion processes that create the planets in the solar system and in all exoplanet solar system. What is the name we're using for this now? Is it exosolar system? I don't even know. I should ask someone.
Closest we've gotten to anything is early formation of rocky bodies in the early solar system.
Right, but how do we call it? How do we call a system of exoplanets? Is it an exosolar system?
Oh, sorry. I don't know.
I don't know the correct terminology. I should go ask a Kepler scientist. I feel like this is something I should know. All right.
Exosolar system.
Exosolar system. We're gonna use that for the next few minutes until somebody corrects me in the comments. Yeah. So what other? I don't remember off the top of my head what other activities we have other than the misconception cards, which we'll get into in a bit. What other gravity stuff do we have on that day?
So the first thing is doing the old Galileo, or possible whether or not he actually did this is, I guess, not totally known. for sure. But it's claimed that he did this. He went up to the top of a tall tower and he started dropping things
The
from
Leaning Tower of Pisa
tower.
in
Right.
particular.
So something many other people have done since then in the name of science. So he was looking at falling objects and comparing how things behaved when they fell from a great height. And so sort of a mini version of that is one of the first activities. This is something you can do with your students. You can have them, first of all, talk about and think about, what happens when you drop objects of different weight or different mass, different shape, different size, all kinds of things. So to start to elicit the ideas that they have about falling objects and about gravity, because that's a really important part of education, is to look at what people are already thinking, because we don't just dump information into people's heads, into their empty heads.
What?
Because it would just be too easy that way. People already have ideas about gravity, and of course, growing up on planet Earth, we deal with gravity every day. So, we have a lot of ideas, for better or worse, about gravity that we come into the classroom with. So your students are going to have all kinds of interesting ideas, and you need to sort of get them out there before you can really start to have them learn.
Ah! I fell out.
Quad